Hello. So, in this lecture as well, we will be talking about a numerical example and try to find out the free vibration response of a 2 degree of freedom system. So, let us try to get into the problem. So, I have a 2 degree of freedom system. The mass and stiffness matrix of the system is given. The two natural frequencies which we can of course evaluate from K and M matrix, but just to shorten the problem, we have already given the value of the two natural frequencies omega 1 and omega 2, as well as the two mode shapes are also given. However, the mode shapes are not mass normalized. So, the problem is that we need to find out the response of the system because of these two initial conditions given. The first initial condition is the initial conditions on the displacement. We are saying that the displacement, the initial displacement, that is the displacement at t equals to 0 for both the degrees of freedom, that is u1 and u2 are 0.5 and 1.0. So, at t equals to 0, the degree of freedom 1, that is u1, is having a value of 0.5 and the degree of freedom 2, that is u2 0, is having a value of 1.0. On the other hand, the two initial velocity, that is u1 dot and u2 dot at t equals to 0 are given as 0. So, there is no initial velocity, however, there is an initial displacement which is given. So, the problem is to find out the free vibration response of this system. So, let us try to find out the free vibration response. So, we have seen that the free vibration response can be written as u1t, u2t using modal expansion theorem. We have talked about the theory of this earlier. We are just going to implement this in this numerical problem. So, we have said earlier by using modal expansion theorem that any arbitrary response of a multi-degree of freedom system can actually be written as a linear combination of the normal modes of the system. So, since this is a 2 degree of freedom system, we have two normal mode and any arbitrary response is a constant C1 into first normal mode plus C2 into the second normal mode. Okay. So, how do we represent the normal mode? I will have C1 into R1, that is the first mode shape, into cos omega 1 t minus theta 1, because it is a free vibration problem. So, this we have talked about in detail in the earlier lecture. So, similarly, I have C2 into the second mode shape, which is R2 into cos omega 2 t minus theta 2. So, omega 1 and omega 2 are the two natural frequencies, theta 1 and theta 2 are the two phase angles. So, if I write it in expanded form, it is going to be C1 into the first mode shape, which is 1 1 into cos omega 1 t minus theta 1, and then I have C2 into the second mode shape, that is minus 1 and 1 into cos omega 2 t minus theta 2. Now, we see that in this expression of the response we have 4 unknowns. So, the 4 unknowns are C1 is not known, C2 is not known, theta 1 is not known and theta 2 is not known. And we have 4 initial conditions, that is u1 0, I have u2 0, I have u1 dot 0 and I have u2 dot 0. So, I have 4 initial condition and 4 unknowns, and we therefore can easily solve this problem. So, let us go ahead with the problem solving. So, the initial condition u1 0 and u2 0 can actually be written as C1, the first mode shape, which is 1 and 2. So, cos omega 1 t is equal to 0. So, I have minus theta 1 and then I have C2, the second mode shape, which is minus 1 and then I have cos of minus theta 2. Right. So, this can actually be written as C1 into 1 2 into cos theta 1 plus C2 minus 1 into 1 into cos theta 2, and that is equal to the given value of u1 0 and u2 0, which is 0.5 and 1.0. So, if I try to solve this equation, this matrix equation or this vector equation is going to give me C1 cos theta 1 plus minus C2 into cos theta 2 is equal to 0.5. And the next equation that I am going to get is 2 C1 cos theta 1 plus C2 cos theta 2 is equal to 1.0. So, if I try to solve this equation, I am going to simply add this 2 and then I am going to get C1 cos theta 1 is equal to 0.5. And then by substituting here, I am going to get C2 cos theta 2 is equal to 0. So, this is the solution that we are getting out of this 2 equation. So, let me just write it. C1 cos theta 1 is equal to 0.5 and C2 cos theta 2 is equal to 0. So, these are the 2 solutions that I will use later. Now, let us go to the second part. So, I will have u1 t and u2 dot t can actually be written as C1 minus omega 1 into R1 sin omega 1 t minus theta 1 and then minus omega 2 C2 R2 into sin omega 2 t minus theta 2. So, putting the value of t equals to 0, I will get u1 dot 0 and u2 dot 0 as minus omega 1 C1 R1 into sin of minus theta 1 and then minus omega 2 C2 R2 sin minus theta 2, and that is equal to 0 0 because the initial velocities are given to be 0. So, this can actually be written in expanded form as omega 1 C1 R1 is 1 and 2 into sin theta 1 minus omega 2 C2 into 1 minus 1 and 1, and this can be written as sin theta 2 is equal to 0 and 0. So, if we solve this equation, I am going to get omega 1 C 1 sine, sorry, this is going to be plus because minus theta 2 goes here. So, I have sine theta 1 plus omega 2 C 2 minus of this C 2 into sine theta 2 is equal to 0. And the other equation is 2 omega 1 C 1 sine theta 1 plus omega 2 C 2 sine theta 2 is equal to 0. So, if we solve this two equation, I am going to get C 1 sine theta 1 equals to 0 and C 2 sine theta 2 is equal to 0, right. So, these are the two sets of equation that I am getting. Now, using this set of equation and this set of equation, I need to solve for C 1, C 2 cos theta 1 or theta 1 and theta 2. So, what I do is that I square this equation and this equation. So, I get C 1 square into cos square theta 1 plus sine square theta 1 is equal to 0.5 square. So, which implies that C 1 is equal to 0.5. So, similarly, from the second equation I can get C 2 is equal to 0. So, C 2 goes equal to 0 and C 1 is equal to 0.5. So, if C 1 is equal to 0.5, cos theta 1 is equal to 1, which gives me the value of theta 1 to be 0 or for the matter of fact m pi, where m could be all the positive number, all the even numbers. So, now if this is the solution, so we can actually get rid of this and we just can say that theta 1 equals to 0 is going to be a solution, because all other even multiple of pi is also giving us going to go back to the same phase. So, it is almost equivalent to take theta 1 equals to 0. So, if we assume this, then we get the solution as u1 t and u2 t as C1 is 0.5, R1 is 1 and 2 and then cos omega 1 t, theta 1 is equal to 0. The C2 part, which is C2 into R2 into cos omega 2 t minus theta 2, this C2 is equal to 0. So, this whole thing is this whole part of the solution is going to 0. So, what does this physically mean? So, I know omega 1. So, omega 1 is root over k by 3n. Okay. So, therefore, I can say that my response, my free vibration response for the given initial condition is 0.5 into 1 2 into cos of root over k by 3m t. So, this is the final response of the system. This is the answer. Now, physically what does this imply? C2 equals to 0 implies that my second normal mode is not participating in the motion. So, the free vibration in this case is essentially only the first normal mode. Therefore, the response is going to be a sinusoidal function with the frequency being the first natural frequency of the system. So, in cases where C2 is not equal to 0, we will see the response as a linear combination of the first mode as well as the second mode, and then the response will be a sinusoid having two frequencies, the first natural frequency and the second natural frequency, or it would be the superposition of two sinusoidal function with the two natural frequencies. One more thing that should be noted here, that though we have talked a lot about finding out the mass normalized mode shape, so that the product of the modal mass normalized modal matrix into mass matrix into the phi is equal to 1. Here for particular this case, we did not bother to mass normalize the mode shapes. We use the mode shapes as it was given. So, I wish to say here that even if we had mass normalized the mode shape, we would have got the similar answer. So, one can try this for themselves and see that even if we mass normalize the mode shape, we will eventually going to get this answer. So, mass normalization is not, we have not done mass normalization here because it would not have proved very computationally efficient. But from the next lecture onwards, I will be solving problems where it would be shown that mass normalization of the mode shapes or the modal matrix becomes very useful and makes the solution of the problem very simple. So, from the next lecture onward, we will talk about generalized coordinate system or natural coordinate system, and we will be talking about how to solve a force vibration problem using the concepts of modal expansion theorem and naturalized coordinate. Thank you.